You ever wonder how your phone can find one specific contact in a list of thousands in, like, a split second? Well, it's not magic, right? It's actually the secret weapon that powers pretty much our entire digital world, sorting algorithms. So today, we're going to pull back the curtain on how computers cleverly create order out of complete chaos. I mean, just think about it. Your daily life is filled with this stuff. Finding a song in a massive playlist, seeing products sorted by price online, even just scrolling your social media feed. All of this depends on data being sorted. The challenge, though, is that computers need a crystal clear set of instructions to turn that jumbled mess into something we can actually use. And that is where an algorithm comes in. As you can see right here, it's basically the recipe, the path that guides the process from a chaotic input to a nice, orderly output. Sorting algorithms are the specific recipes computers use to arrange data, and today we're going to explore some of the most famous ones out there. Okay, so before we get into the how, let's really lock in the why. I mean, when we're dealing with these huge amounts of information, speed is absolutely everything. Sorting is often the very first, most critical step in making that data searchable, manageable, and super fast to work with. So at their core, these are really just different strategies for lining things up. Numbers, names, dates, you name it. But, and this is a big but, the strategy you choose can have a massive impact. Picking the wrong one, man, that can be the difference between a task that takes seconds and one that takes hours. All right, let's start our journey with two of the most intuitive algorithms. They're pretty easy to wrap your head around, which makes them a fantastic place to begin. But as we're about to find out, their simplicity comes at a cost, and that cost is speed. First up, bubble sort. And honestly, the name is perfect because it literally works by slowly bubbling the largest elements up to their correct position at the end of the list. It's wonderfully simple to visualize, which is great, but it's also one of the least efficient sorting methods out there. So here's the game plan. You look at two numbers right next to each other. Is the one on the left bigger? Yep. Okay, swap them. Then you just slide over to the next pair and repeat that exact same process all the way down the line. To really see how this works, let's just walk through an example. Okay, so check this out on the screen. We start with our list. First, the algorithm compares 9 and 5. Well, 9 is bigger, so they swap places. Next up, it looks at the new neighbors, 9 and 8. And again, 9 is the larger number, so they trade places. You can already see the 9 starting its little journey over to the right. And the process just keeps on going. 9 is compared with 3, and they swap. Then 9 meets 1, and they swap one last time. Now, this is the crucial part. After just one full pass through this list, the largest number, our 9, has bubbled all the way to its final sorted position. The algorithm then just repeats this whole process over and over for the remaining numbers until the entire list is in perfect order. So while bubble sort was all about those little local swaps, our next foundational method, selection sort, has a completely different strategy. Instead of just comparing neighbors, it scans the entire list to select the absolute smallest item, and then it puts it right at the beginning. The best way to think about it is like sorting a line of people by height. You'd scan the whole line, find the shortest person, and tell them, hey, you, go to the very front. Then you just ignore them and repeat the exact same process for everybody else left in the line. That's selection sort in a nutshell. It's methodical, and it actually makes fewer swaps than bubble sort, but boy, it still has to do a lot of scanning. Okay, so we've seen the kind of brute force methods, but what if we could be a bit more clever about this whole thing? Let's look at an algorithm that I bet many of us have used without even realizing it every single time we pick up a hand of playing cards. This is insertion sort, and it's actually pretty brilliant. Imagine you're being dealt cards one by one. You hold that first card. When you get the second, you place it either before or after the first one, right? For every new card, you just scan the ones already in your hand, which, by the way, are already sorted, and you find the correct spot to just slide it right in. You're building a sorted section, one element at a time. Now, what's really cool about this method is why it can be so fast. If your data is already almost sorted to begin with, insertion sort is an absolute superstar. It only has to make a few little adjustments to get everything into place, instead of doing a ton of unnecessary work. It's really the perfect tool for small lists or lists that are nearly in order. So, these simple algorithms are great for learning, but they just don't scale. When you have millions or even billions of items, you need a fundamentally different strategy. So, enter divide and conquer, a seriously powerful approach for solving huge problems by breaking them into smaller, bite-sized ones. The logic here is pure genius. Don't try to sort one massive list all at once. Instead, you just split it in half, then you split those halves, and you keep going and going until you have these tiny problems that are super easy to solve. I mean, a list with just one item in it, that's already sorted, right? Then you carefully merge those solved pieces back together in a way that preserves the sorted order. And this slide right here perfectly illustrates merge sort in action. Just look how the unsorted list at the top is broken down again and again and again until each number is in its own little list. And like we said, a list of one is already sorted by definition. Then the algorithm begins the conquer phase, merging them back together, two at a time in the correct order, until you're left with one final, perfectly sorted list. Now, our final algorithm, quicksort, also uses this divide and conquer idea, but it's got a different twist. Instead of just blindly splitting the list in half, it intelligently picks one element to be the pivot. Then, it rapidly rearranges the list so that all the numbers smaller than the pivot are on its left, and all the numbers that are larger are on its right. Just take a look at this example on screen. The number 100 is chosen as the pivot. The algorithm then just zips through the list, shuffling everything around it. And notice how, after this single partition step, all the numbers to the left are smaller than 100, and all the numbers to the right are larger. And just like that, the pivot, 100, is in its final sorted position. The algorithm then just repeats this same process on the two smaller subarrays on either side. So we've seen 5 different strategies, from the simple and kind of slow to the fast and pretty complex. This, of course, begs the ultimate question: which one is the best? And the answer, as it so often is in computer sciences, is, well, it totally depends on the situation. So the crucial thing to understand here is efficiency, which we call complexity. Just look at this graph. That steep upward curving line labeled ON squared, that's our quadratic time algorithms, like bubble sort. Here, n is just the number of items. That squared part means if you double the items, the sorting time roughly quadruples. It gets slow really fast. But look at that much flatter line, ON log n. Those represent our divide and conquer algorithms. They scale far, far more gracefully as you add more data. Let's just put it all together on this handy summary table. Bubble and selection sort are O of n squared, which makes them pretty slow for large data sets. Insertion sort is also O of n squared in the worst case, but like we said, it's got that special talent for nearly sorted lists. And then we have our divide and conquer champions, merge sort and quicksort. They're both O of n log n, offering consistent, fast performance, with quicksort often being the fastest of all in most real-world scenarios. So at the end of the day, there is no single best algorithm. It's all about these trade-offs. Are you sorting 10 items or 10 billion? Is your data totally random? Or is it mostly in order? Do you have lots of computer memory to play with? The answers to these questions are what will point you to the absolute perfect tool for the job. Look, understanding these fundamental building blocks is more than just some abstract theory, right? It's about learning to solve problems efficiently and elegantly. It's knowing the best way to bring order to all that chaos. So the next time you face a mountain of messy data, which of these superpowers are you going to choose to wield?